Oh, hi. What I want to do, I want to make a effects pedal for my wife's electric violin. And I'm thinking it's going to have some distortion, just a very light, nice sounding distortion. It's going to have a delay, like an analog bucket brigade delay, and a phaser on it. That's what I'm thinking. And I think that'll work really nicely for electric violin. And I want each of these circuits to work for the electric violin. My friend Ian lent me these guitar pedals, these classic guitar pedals here. Here they are. So the fuzz face, which is sort of two germanium transistors, the Ibanez tube screamer, and this one here that's back to front, that's now the right way around, the Hendrix octave fuzz. So what I thought, these are sort of well-known units. The circuits for them are out there and published. You can find out how they work. But what I thought is I want to know sort of what the signal looks like that comes out of them and as compared to how they sound. So what I'm going to do is I'm going to connect a sine wave up to each one of them, a low frequency, a mid frequency, and a high frequency sine wave, and just record what the waveform looks like. So let's do it. So just to review the test setup, obviously I've got a oscilloscope and a signal generator, but they really didn't work very well, and they don't kind of give you a picture of the sound that it makes at the same time. So what I've got is I've decided to use instead as a signal source my synthesizer, and then it's going into this sound card, and then it's coming back out of the sound card into the device under test, and then it's going back out of the device under test back into the sound card again, and the whole thing's getting recorded on an instance of Cubase. Now the only problem with this setup is that you don't get quantitation, you don't actually get the levels, so I'm going to double check the levels using one of those gadgets. So in the end I included a oscilloscope in my test setup. It just seems to be the best way to get the thing done. So I've got the oscilloscope, I've got Cubase, I've got the synthesizer, I've got everything. So here's the input signal. Here it is, it's a nice sine wave, well almost a sine wave anyway. This one, as you can see, 7.3 volts peak to peak, and 65 hertz, which makes it the 2 C's below middle C, so 2 octaves below middle C. This is what the output looks like, and that's what it sounds like. As you can see, it's a pretty ugly looking square wave, which has been bandwidth limited. It looks like there's a capacitor on the output there. If I muck around with these knobs here, it really doesn't make much difference, except that this one here marked in just changes the amplitude of that output. Now if I change the size of the input, so just decrease the input, something interesting happens. I get to here, I get this very nice sound. I mean, it's a very sort of fluty, reedy sort of a sound. And then if I go lower than that, it just collapses and you don't get anything anymore. Okay, so this time around we've got 220 hertz, so that's the A underneath middle C. I'll just turn the input up. And once again we've got this really pretty ugly looking signal, an ugly sounding signal. If I turn the input down, again we get to this zone where it starts to sound really nice. And just to measure that, so that input voltage there, look at how noisy it is. is sitting around peak to peak 40 millivolts, so quite a small input signal to get that nice sound. Okay, so this time around we've got 2 Fs above middle C. It's about 699 hertz, and this is what it sounds like. And again, fairly ugly sound. And when we turn it down, turn the input down, well, but basically back to a sine wave. But just before that, we get a little bit of sort of sawtooth wave distortion before it really squares off. So next up, I've got the Ibanez tube screamer. When I first put this device up, it wasn't really working properly, so I had to pull it apart and understand what had gone wrong. Not unsurprisingly, it's the foot switch is broken. I think that's probably familiar to anybody who owns one of these. I'll just turn the input up. So I've got, again, 2 Cs below middle C, so it's 65 hertz. So this is with the thing off. It's just a momentary contact switch. So if I just provide a momentary closure there with a screwdriver, there it is on, and here it is off. Interesting thing with this device is that it's not really a true bypass. So if I turn the input signal up, it's about at about 4.6 volts peak to peak, it does that. So it just squares it off on the bottom. I mean, obviously with a 9-volt battery, you can't carry a signal that is much more than about 4 volts peak to peak and keep the electronics running. But that's pretty nasty. But then again, I don't know that there's many guitar pickups that would produce a signal that's bigger than 4.6 volts peak to peak. Onwards. So here's our distorted signal. It's like a triangle wave, isn't it? It's a bit more subtle than what we've seen before. Let me turn the drive knob up. That triangle kind of starts to look more and more like a sawtooth wave. And we hear some more harmonics as well. The tone knob just really knocks off those higher frequencies for us, and the level is just controlling the level. No real magic there. And as we turn the input level down, the output waveform remains pretty well the same until it just collapses right off. Okay, here we go at 220 hertz. That's the A below middle C. It sounds like this. And the tone knob sounds like this. And the drive sounds like this. Not a lot of difference there. Onwards with 699 hertz. It's the F above middle C, so 2 Fs above middle C. It sounds like this. And I'll just take the drive down. Doesn't really make any difference. And the tone. Yeah, the tone makes quite a bit of difference. So it's obviously attenuating at a frequency, well, that's about half, isn't it? So the 3 dB point must be around 700 hertz. Yep. Okay, great. Well, that's it for the tube screamer, I think. Okay, here we are with the Hendrix octaver, and we're at 65 hertz, or that's 2 Cs below middle C. And well, the first thing to note about this one is, so I've got a 5.5 volt peak to peak signal going in. If it's much bigger than that, look what happens. So this is on bypass. So if I go much bigger than that, whoa, that's on bypass. So again, the bypass is not a true bypass, it's an electronic bypass. So we'll just reduce that down, so we just take that out of there. We'll put the thing on again, and here's the signal that we get out of it. Pretty and there's the characteristic octave doubling effect. If we turn the tone up, we get a little bit more high frequencies. It's a fairly subtle effect. I think the tone must be before the processing. And then the volume control is really just a level. Nothing too interesting there. If I turn the input down, here we go. This is the sort of effect I get. Sort of just gets softer and softer, and then just disappears away. Okay, so let's onwards up to A220. I think that's the A below middle C. We'll just tune it up. There we go. Take our test input down just a tiny bit, just to make sure it is actually a sine wave coming out or going in. And here's our process signal. That's the tone up, tone down, tone back up again. And now I'm going to reduce the input. Input down. And, well, let's go up to 700 hertz now. There we go, 699 hertz. So that's the, I think it's 2 Fs above middle C. Tone control. Yeah, lost my trigger. Sort of a different sort of a shape and effect at this frequency, isn't it? Really, because of the timing. Alright, so I'll turn that right up. And now we'll change the input volume. Just turning it down. Okay, so there we have it. That's the Hendrix octave fuzz, and that is the end of our measurements.